Today we're going to start chapter 12. So this is video lecture number 1, and it deals with states of matter. The states of matter are solid, liquid, and gas. We're going to apply this to what we call the kinetic molecular theory. Kinetic energy is energy of motion. So the kinetic molecular theory states that particles are in constant motion. They have kinetic energy. We're going to apply this to all three phases, but today we're going to concentrate mostly on gases. So the kinetic theory applied to gases states, number 1, a gas is composed of small particles that have insignificant volume and are relatively far apart. So the volume that the particle occupies is very, very small compared to the space it's found in. Between the particles is empty space. And the theory states that there is no attractive or repulsive forces between the particles. So if they get near each other, they will just pass by each other. Number 2, the particles of a gas move in random, constant motion in straight paths. So a gas particle will travel in a straight line until it hits something else. This causes gases to fill their containers, regardless of the container's shape or volume. Also, all collisions are perfectly elastic, which means that when a collision occurs, all of the energy is transferred without any loss from one particle to another. Number 3 states that when a substance is heated, the particles will absorb energy. The absorbed energy will speed up the particle, which increases their kinetic energy. An increase in kinetic energy will increase the temperature of the gas. The particles in any collection of atoms or molecules have a wide range of kinetic energies. Some move relatively slow, some move relatively fast, but overall there is an average kinetic energy that we will then use to describe the gas. So remember, a couple of the particles move slow, a couple of the particles will move fast, but overall there will be an average. And this is extremely important. Temperature is a measure of the average kinetic energy of the particles in a sample of matter. If you increase the average kinetic energy, it's because there was a temperature increase. As a substance cools, the particles slow down and their average kinetic energy declines, which means their temperature will also go down. The Kelvin temperature of a substance is directly proportional to the average kinetic energy. So helium at 200 Kelvin will have twice the kinetic energy as helium at 100 Kelvin. So if you double the temperature in the Kelvin scale, you will double the kinetic energy. All substances at the same temperature have the same kinetic energy, whether you are a solid, a liquid, or a gas. The temperature at which all motion theoretically ceases is 0 Kelvin, which is minus 273 degrees Celsius, which is called absolute zero. How do gases behave? Gases have low density. Gases expand and compress. And gases diffuse, which means that they mix until they are evenly distributed. Gas pressure is the result of collisions of billions of gas particles with an object. If there are no gas particles present, there is no pressure and a vacuum exists. The gas pressure we're most familiar with is atmospheric pressure. Air exerts pressure on the Earth because gravity holds air molecules in. So the closer you are to the surface of the Earth, the higher the pressure. Atmospheric pressure decreases as you climb a mountain because the air thins out as the elevation increases. Barometers are instruments that we use to measure atmospheric pressure. Pressure is also weather dependent. So a low pressure usually signifies warm air coming in, and high pressure indicates colder air coming in. The SI unit of pressure is the Pascal. Atmospheric pressure at sea level is about 100.3 kilopascals, which is from reference table A. There are two older units that we use that you may see in a question, millimeters of mercury and atmospheres. So we have some proportions we can set up. 1 atmosphere is 760 millimeters of mercury, which is 101.3 kilopascals. And now we're going to start looking at some of the gas laws. The first law, not too hard, is Dalton's law. Each gas in a mixture will exert pressure as though it is independent of the other gases. So P total, the total pressure, is just the sum of the individual pressures. So we're going to finish with two problems. What is the partial pressure of hydrogen gas in a mixture of hydrogen and helium if the total pressure is 600 millimeters of mercury and the partial pressure of helium is 439 millimeters of mercury? So P total is equal to the pressure of the hydrogen, remember it's diatomic, plus the pressure of the helium. The total pressure is 600. We're looking for the partial pressure of the hydrogen, and the pressure of the helium is 439. So pretty simple. The pressure of H2, subtract 439 from each side, and we get 161 millimeters of mercury. And the second problem, find the total pressure for a mixture of 4 gases. Notice we're changing the unit, but it doesn't change the problem. P total is equal to one gas is 5.00, another gas is 4.56 kilopascals, another is 3.02, and another is 1.29. So the total pressure is just the sum of the individual partial pressures, which is 13.87 kilopascals. And that's it for today. So we will see you in class tomorrow.